Hello folks, and welcome to the channel, or welcome back to the channel. And this is part 2 Bravo, where we're going to reassemble the Weber carburetor that we took apart in part 2 Alpha. In part 1 we explained the working of the carburetor, but now we're going to build a new baseline for this carburetor. So let me explain you what that is, a new baseline. How many times have I heard people say, oh, I'm going to get a Weber carburetor and I'm going to fit it on my car. And they do so, and then they're so disappointed because it just doesn't perform. And the reason for that is that the carburetor is not fit for purpose and not fit for use for that specific vehicle or that specific engine. And this is what we're going to do now. Setting a proper baseline defines all the jets, the venturis, and all the other parts on the carburetor that will make that carburetor fit for purpose and fit for use on your specific vehicle. I have here a Pinto engine which is tuned, and I'm going to create this Weber carburetor. I'm going to dimension it, I'm going to baseline this carburetor, and therefore you need to know a couple of things if you're going to build a carburetor, because the first thing you need to know is how big does my carburetor has to be. And for that we need to determine the main venturi. And here it is, the main venturi. Now the question is, how do you know what size you're going to need? So the size of your main venturi will also decide the size of the barrel of the carburetor. If you need a 40 DCOE, a 45, a 50, a 35. But don't worry, we'll go through all this. So the first thing you need to decide is, what type of an engine do I have? Now, I'm going to do this exercise here on this specific Pinto engine, and I need to know what is going to be my maximum RPM I want to run this engine. And in my case, that's going to be 6,000 RPMs. How much horsepower will it develop? Well, I aimed and I tuned it and I modified it to about 150 horsepower. And then finally, you need to know the displacement of the cylinders. What's the volume of an individual cylinder? And is my carburetor going to feed each cylinder individually? Maybe you have a twin barrel carburetor that's going to feed 2 cylinders, so it's one carburetor in essence to 1 cylinder. Or maybe you just have a twin barrel which is feeding 4 cylinders. So these are the things you need to decide up front. The second thing is that you need to decide for what kind of purpose you're going to use the vehicle. Are you going to use it for your daily commuter? Maybe you do. Or are you going to use it for fast road? Or maybe you want to use it for racing purposes. Different things, because if you go into race, you're going to rev it up very high, so the venturi has to be different. If you're going to use it as a fast road, then you're more interested in the mid-range RPMs where you want to have the power. And a daily car is probably mid-range to low-level RPMs. That's where you want to have the torque. So these things are important. So when I say fit for purpose and fit for use, that's the decision you have to make. What type of an engine, what are the specs of my engine, and for what purpose do I want to use that engine? So now let's look on a graph. So first thing to do, decide the size of your main venturi, because that will also determine what size of carburetor you need. Because the barrel is limited. If you have a 40 DCOE, then the barrel is only 40 millimeters. So you cannot fit a main venturi then which is bigger. So you need to consider that. So let's look on the graph. I made a graph here whereby you see on the vertical axis, you see the main venturi in millimeters. So a 50 and a 20, 25, 30 and so on. And horizontally, you see the cylinders, volume. So what's the displacement in a single cylinder? I listed that as cc's, cubic centimeters. But of course, it could be anything else in the US and cubic inches and so on. So the engine I have is a 2-liter Pinto, and I have 4 cylinders, meaning that I have 500 cc per cylinder. And I'm working on a curve which I looked at before, and I remember that I just said a few seconds ago, I want to rev up to about 600 RPMs. That's where I want to get at full throttle. I don't want to go higher than that, but I want to achieve 6,000 RPMs. But maybe you want to get 8,000 RPMs if you're more into rally racing. But if you're really into track racing and high-speed racing, you might want to have 10,000 RPMs. So what I did is I drew a couple of curves for the 6,000 RPM, the 8,000 RPM and the 10,000 RPM. Now that we know what the volume of the cylinder is, we can actually go up where we meet the line, and here's the point. This is the point where we meet, and then look horizontally, and then you can find what your main venturi should be. And in my case, this looks like 36 millimeters. So that's going to be my main venturi. But of course, if you wanted to rev that engine up to 8,000 RPM, look at this, then you would need probably about a 46 millimeter venturi. So now you can see, if I wanted to rev up the engine up to 8,000 RPMs, I wanted to achieve it with this carburetor, I couldn't, because my carburetor is only a 40 DCOE. And I can't fit, of course, not a 46 millimeter venturi in it, because my main barrel is only 40 millimeters. So that's what I'm stuck with. So, and because I already have the carburetor and it's a 40, I stayed on the 6,000 RPM curve. But of course, for you, that could be a bit different on your specific engine. Let me show you the barrel and then the venturi on how that fits in there. This is our cleaned 40 DCOE carburetor, and the 40 refers to the opening of the barrel. Let me measure that for you so you can actually see it. Here you go. It's exactly 40. So the main venturi is going to fit into the carburetor, but let me first of all measure the one that I have right here. So we calculated that I'm going to need about 36 millimeters for my engine to perform. So let's measure that. And as you can see, this is about 36 millimeters. Now the main venturi fits in, very simple, like so, and just it falls in. If I would have wanted to rev up to 8,000 RPMs, then I would have needed a 46 main venturi. And as you could see, that doesn't fit in my 40 DCOE. Now of course, if you don't have a carburetor yet, then you have far more free play. And then you can select the proper size of carburetor and the proper venturi. Now a little bit more about the venturi itself. So you probably wonder, where the hell do you get these charts? Well, these charts coming out of manuals, a tuning manual from Weber, and it has all kind of graphs and explanations in it. Very good book to get, and I'm not making a commercial for this book, but it's worthwhile getting it, because that's where you find the graphs, and that's where you find more details on all the different jets and what you can order and all the part numbers. So I really recommend that you get a book like this, and there are many different types of them, but this one is a very, very good one. So keep that in mind. And again, I'm not making a commercial for this magazine or this book. I just want to make one more point very clear, that baselining is not the final tuning. Baselining is your starting point, where the carburetor will work properly with your engine, and from there on you will have to do some more fine-tuning. But if you don't get your baselining right, then forget fine-tuning of your carburetor. It's never going to work. Now fine-tuning is going to happen on a dyno or on a road test, but this is not for this video. That will be in part number 3. Now that we have determined our size of our main venturi, we now need to have a little chat on why you need a certain venturi. What is the difference on a small one and a large opening? Because that is important to know, because by that you will understand why you need to fit a certain type. So let's use the board for another minute or two. So let's dig in a bit deeper into the main venturi, and this is the main venturi. And to be very honest, this is not really a venturi. It is just a funnel or a yoke that makes the opening smaller or bigger. The secondary venturi, that's the one where the main jet is feeding fuel into. And both are mounted in cascade inside the barrel of the carburetor. So first you have the main venturi, followed by the secondary venturi. And the main jet is feeding into the secondary venturi. So the whole purpose of the main venturi is to create sufficient vacuum so fuel can mix with air if there is enough vacuum. So we need to have sufficient airflow through the barrel of the carburetor to create that vacuum. So now imagine that we have a carburetor with a main venturi which is fairly large, wide open. On this side we have the engine, so the cylinder which is sucking in air, and on the other side we have the air intake. So air will flow through the carburetor, through the main venturi, and while it's flowing into the cylinder, it's going to create a vacuum right here at the secondary venturi, and the main jet or the main circuitry will start kicking in and fuel will be mixed with air. Now that is only going to happen if there is sufficient airflow, because we need to have sufficient vacuum to suck up that fuel. And sufficient airflow means sufficient air speed. So we need to increase the air speed. Now on low RPMs the air speed is fairly low and the main circuit is not going to kick in very quickly. It's only at higher RPMs that it's going to kick in. Now if we were to install a smaller main venturi, then this opening here becomes a lot smaller than what we had here. And as a consequence, if the engine is running on the same RPMs in both cases, air which is going to come through will accelerate, because the same amount of air has to pass through the system. And because the acceleration of the air speed increases, and the vacuum that's going to be created increases tremendously. And therefore, smaller venturis or smaller main venturis will force the main jet to kick in earlier. So it is ideal if you're going to use the car for road use and maybe fast road use. If you're going to race on a racetrack, then you don't want to have a narrow main venturi, because you're going to do a lot of RPMs, and a lot of RPMs means a lot of air needs to be sucked in within a certain time, and that means the air velocity will increase automatically by itself. The airspeed will be much larger on high RPM, so therefore the venturi effect will work just properly. If you were to put in a narrow main venturi for race purposes, then you're going to have a restriction, because you're not going to get all the air into the cylinder that you're going to need, because you narrowed it too much. So that's a bit the story. So the main venturi is a balance between size, airflow and airspeed, and the smaller the main venturi is, the sooner the main jet system will kick in, but the more constrained the airflow is. So keep that in mind. So now let's talk about the secondary venturi and the main jet. So far we dimensioned the main venturi and the size of the carburetor, which is a 40 DCOE. Now it's time to talk about the main jet, the secondary venturi, and of course the emulsion tube and the air reduction jet. All very important, that all work together on your main circuit on your Weber carburetor. So let's have a look first of all at the secondary venturi. This is a secondary venturi, and I taped it off to a light source, and inside you can see the bright spot there. This is your secondary venturi opening. The size of the secondary venturi is typically stamped at the bottom of the venturi, and this is the 3.5. Now this model is the old model with the spring loaded, so you just push it in and it's held in place by the spring. Newer models actually are held in place with a screw. You might remember that I had two different types fitted in this carburetor when we started, 3.5 and a 4.5. But now I ordered up a spare part, and here it is. This is the spare secondary venturi. And now I can fit this one, and it's the same 4.5 millimeters. I know that they're not exactly the same, especially the outer side is a bit different. Diameters are alright, they are exactly the same diameter, but there is no edge on this one, and this one has this nice edge or rim. So right now we're going to fit the secondary venturis, and this opening right here leads into the center point of the venturi, and that's where the fuel will come in from the emulsion tube. There's a groove here, so make sure the spring goes in the right side, and then you position it like this so that this opening points to the opening in the carburetor. That's it, and then we do the other one. Done. You might notice that this ring closes all the way up to the front, and here it doesn't. It's not going to fall out. That's just because this is a probably an aftermarket secondary venturi, although I did buy it as original, but it doesn't look to be the same. But that's all right. I can always place a washer here or a ring if that was necessary, but that is not really necessary at all. So you're probably going to ask me now, which secondary venturi should I put? A 3.5, a 4.5, or a 5? Well, a good all-rounder is a 4.5, and they're easy to remove and put another one in if necessary. But 4.5 is going to work for most applications. And remember, the 4.5 is the actual opening inside where the fuel comes out. But the real determining factor is your emulsion tube and your main jet and your air reduction jet. And that's the next thing we're going to talk about. This is an emulsion tube, and I drew it on the board so we can get a bit of a better understanding. It's a hollow tube with orifices drilled into it. There's orifices at the bottom, in the middle, and on the top. And sometimes they shift position depending on what type of emulsion tube you're going to fit into your car. There are different types, different models for different purposes. On the top you will find an air reduction jet, and on the bottom you'll find your main fuel jet. So fuel is going to come in from the bottom because this tube is sitting in the well of the carburetor, and there's a certain fuel level which you need to maintain with the float. That's why the float becomes so important. So fuel will be sucked in from the bottom, air will come in from the top, and they will mix, and that's what we then call an emulsion, and then it's going to be sucked out through the secondary venturi into the barrel of the carburetor and then into the cylinder. So now it is very important to identify three things. We need to identify the type of the emulsion tube. That's important. We need to define the main jet, and we need to define the air reduction jet. Those are very important factors. Now, the air reduction jet is very simple to define because that's typically 50 hundredths of a millimeter bigger than your main fuel jet. So that's kind of a common standard to start working with. The bigger the air reduction jet, the leaner the mixture becomes at high RPMs. The smaller the air reduction jet, the richer the fuel mixture becomes at high RPMs. It has no effect on, or almost no effect on, low RPMs. On the contrary, the main fuel jet, the larger the opening becomes, the richer the fuel will become at both high and low RPMs, and the thinner or the smaller the opening, the leaner the mixture will become at high and low RPMs. So now you can play with those two to balance the mixture properly to the mixture you want to get. So now let's go through some basic starting points to determine the main fuel jet, and then we'll look a little bit closer to the emulsion tube itself. To determine the main jet, there's a very simple rule. Per 1 millimeter of the main venturi, you have 0.05 millimeter of main jet opening. So if you take, in my case, my main venturi being 36 millimeter, you multiply it by 0.05 millimeters, that's going to give me a certain number, and then I multiply it again by 0.75, which is a factor. I need to do that because my carburetor feeds a single cylinder. If you have a carburetor feeding two cylinders, you multiply it by 0.9, and if you have a carburetor that feeds all four cylinders, you don't need to multiply it at all. So in my case, I ended up with 1.45 millimeters of my main jet, and that's where I have right here. Now that's on the assumption that the air reduction vent is 2 millimeters. Typically the air reduction jet is about 0.5 millimeters bigger than the actual fuel jet. But I'm not going to fit this. My fuel jet will be 1.65 millimeters, so I'm going to run it a little bit more rich, both on the high revs and on the low revs, because that's what the main fuel jet does for you. Here's the emulsion tube, which is an F16. I have a 165 main fuel jet, I have a 175 air reduction jet. Now the main difference between all the different emulsion tubes are these orifices. There are more or less holes. They're higher up or lower down, and they all have a specific purpose, those emulsion tubes. Let me give you a little example. As you can see, there's a whole raft of different tubes available, but the most current ones for a mixture enrichment at low RPMs or during slight acceleration is the F7. You could also use mixture weakening at low RPMs or during slight accelerations. For that one you can use an F2, an F3, an F11, an F14, an F15 or an F16. And some of them have special orifices for high RPM mixtures and richness reductions when the air bleed jet is bigger than 2 millimeters. And in that case, you probably would be going for an F7 or an F8. And then you have special tubes for alcohol-based fuels. So really a lot of options, and therefore you really need to check the manuals out and find out what is the right tube for you. Now, for my case, the F16 is the most common one, and it's a pretty good tube by itself at high RPMs and low RPMs. And in fact, the F16 is for mixture weakening at low RPMs or during slight accelerations. So you might have seen that I'm using a quite fairly large main jet, which will enrich the fuel at low RPMs. But since I'm using an F16 tube, I'm going to reduce that mixture a bit at low RPMs and during accelerations. Now, a lot of that you will have to test out during the actual test run or on the dyno, but a good starting point is always important. So I'm going to use an F16 emulsion tube, which is reducing the richness of the mixture at lower RPMs and at slight accelerations. And I'm doing that because I'm having a fairly big main fuel jet, a 165, where a 145 would actually be enough. So that combination will reduce it. Now, on the other hand, my air reduction jet is not 50 or 0.5 millimeters larger than my main jet. It's only about 0.1 millimeter larger than that one. But that's good enough because a 1.75 is still fairly large enough. So that means that I'm going to be running a little bit more rich at higher RPMs than what I would normally do. But then again, I might have to change some of that during the test rides, and that's what the dyno will show to me, or the road test, if it's good or not. So that's where we are. So it's not always straightforward, but again, if you work on your engine, check it out and go with some standard, a good baseline for those jets, and I've given you some examples on how you can do that. I'm deviating a little bit from the ratio between the main fuel jet and the air reduction jet, but it will still work for me because I've done that before. But if you're not sure about that, just go to the 0.5 millimeter difference between the air and the main fuel jet. So now we can install the main fuel jets. You don't need to lock this down too hard, just gently. There we go. And just remember that the air reduction jet is only affecting the richness of the mixture at high RPMs. The main jet is just the opposite. The bigger the opening, the richer the mixture becomes at high and low RPMs, and the smaller the opening, the leaner the mixture becomes at high and low RPMs. So now let's get on to the next phase, which is actually the idle jet. So now it's time to start talking about the idle jet, and the idle jet is probably a really wrong name for it because it takes care of much more than just idling the engine. Of course it takes care of idle, but it also is involved heavily in the progression of the engine, so when you move from idle to actually higher RPMs, and it also is involved in your cruising speed. So if you're on the highway and you're cruising along, your throttle isn't wide open, so then the idle jet comes into play. Now the idle jet is a combination of an air and fuel jet all in one piece. So let us have a look on that and then figure out what we need to have. And this is the air jet, and it says 50 F8, and if we turn it around, then you can see on the head that's 50 or half a millimeter. That's the fuel jet, and on the side we actually have the air jet, which is that single hole right there. There's only one hole on this one. Some of them have two. So let's have a closer look on what these numbers mean. So a good starting point for your idle jet is to look at the volume of your cylinders. So in my case, I have a 2-liter engine, so every cylinder is 500 cc or half a liter. And according to the tables that you find in the catalogs or the manuals from Weber, you will find out that the 500 cc cylinder is okay with 50 to 55 as a fuel orifice for the idle jet. And the fuel orifice is actually over here all the way on the bottom, and I just showed you on a diagram where it was. And that is the opening, so it's 0.5 millimeters or 50 hundredths of a millimeter, and that's why in the code you will see in the front a 50. If you see another number, then it's a bigger opening, but that is a good opening for a 500 cc. The second part on that idle jet is actually the air jet opening. This is something over here, and either that's one hole or two holes, and that's identified by the second part of the number, which is in this case an F8. And if you look that up in the manual from Weber, or the parts manual, then you can see what that is, and an F8 equates to a 1.2 millimeter. So this is not very lean, it's not rich, it's somewhere in the middle, but if you're going to go and select a proper jet, make sure that you have it for the right volume of your cylinder for the fuel opening, and then try to start with the leanest opening for the air mixture, because that combination will determine your carbon dioxide measurement if you have to go to the technical inspection or so. So you may have to change that. Keep in mind that this jet is a very important jet for your idling and your progression and actually your cruising. So that's about it for the idle jet, but idle jet alone doesn't work on this carburetor. But now that we have sized it, we will install it, and we'll also install the idle mixture screws, because that's another element that comes into play, and the progression holes. So now we can install the idle jets, and we'll also install the idle mixture screws, and always use new ones if you recondition the carburetor together with new springs. Those are not expensive, and it's worthwhile doing it. And the springs go over there, and that's where this goes. Don't over tighten those, that's not necessary. We won't adjust those for the moment, that's something we'll do once the carburetor is installed on the vehicle. There we go. The acceleration circuit in a carburetor is critical in any carburetor, because if it squirts too much fuel straight into the intake manifold, then the car won't move, it will bog. If it doesn't squirt enough fuel, then you have another problem, then you won't accelerate either. So in both cases it is a problem, so we need to go for a proper size. And the best approach is to start with a minimum squirt, and then maybe you might have to build it up. There's a lot of things that interwork with each other, so there's not only the acceleration jet, but there's also the acceleration pump, there's the bleeding valve. All these elements come into play. So let's have a look on how that works and what I'm going to use for my specific engine. These are the components that make up the acceleration circuitry. 2 injection jets that are injecting the fuel straight into the intake manifold, an acceleration pump, and we have the acceleration return valve and bleeding valve. So let us have a look on how all that is now working together and what is supposed to be the right sizing for that. I hope you guys don't get bored too much about all the drawings on the board, but at work I do the same thing, and my colleagues keep telling me, Steve, you're explaining too much sometimes. But okay, anyway. Right, acceleration is critical, right? So you want to squirt sufficient fuel into the intake manifold, not too much and not too less, because either one isn't working properly. It has to be dosed properly, and that's why the acceleration jet has a hole at the bottom, which is actually the hole where the fuel will be squirting out into the intake manifold, and that hole has to have a certain diameter. And for a 500 cc cylinder served by a single acceleration jet, 35 or 0.35 millimeters is a good starting size. You can go a little bit higher to 40 if that's what you want to do, but it's not necessary. 35 really works well. Now, whenever you depress the gas throttle, the acceleration pump, which is based on a plunger, will force fuel into the acceleration jet on the top, and that's why you have those little holes there, and fuel goes down and then it squirts out. But also the acceleration pump has something what we call a bleed valve and an anti-return valve, and that's sitting in the float chamber. It's submerged in fuel, so fuel gets into this valve and then gets into the acceleration pump, and when it's depressed it cannot return because there's a blockage there. However, there is a bleeding hole there on that one, and in my case this is a 0.60 hole that I have on mine. Now that bleeding hole there is to compensate for the jets that you have there. So if it turns out that an acceleration jet of 35 is just not enough, then you can fit a 40, right? But the 40 may be a bit too much. So then you can compensate by getting a larger bleed hole on your bleed valve and return valve. So you can play with that, so you can really tune it very nicely. I think for a basic setup, or our baseline setup, I'm going to go for a 35, and I will have my bleed valve at a 60. Well, it's a 0.60. It's a very, very small hole. And that should be it. So let's install it, and then we'll see what we're going to do next. So the first thing I'm going to install is the acceleration pump itself. And then we just need to depress that, and that should just go in very smoothly. And you can squeeze that a little bit. All right. There we go. Now that's in. So now I'm going to install the return valve, and that's all the way in the bottom of the flow chamber. And that's a bit tricky, so I'm going to try with the pliers to pre-position it, and then use a screwdriver to turn it in. All right. Yep, there we go. That's a bit tricky, but with a bit of patience, you will get it in. The accelerator jets have a small little washer, and sometimes it can be a bit tough to get it off. It is an aluminum type, and here that is. So let's take it off, and we'll fit a new one. Sorry guys if my hands are in the way. Let's try. There we go. So that's on, and now we can actually fit the jet. Now you got to make sure when you fit the jet that the hole is pointing forward into the intake manifold, and that's why you have a flat side here. So let's put that in, and there we go. That's done. Now let's do the other side. And these are the caps for the acceleration jets. There is an O-ring, and this is an old one, but whenever you replace those, you should use 2 new O-rings for that. And now we can cover up the accelerator jet with the caps, with the new O-rings. And again, don't over tighten. You don't want to have a leak, but you don't want to over tighten either. Now we need to install the pump valve weights, and these are very small weights, and here is such a weight, as you can see. And there's also a steel ball that goes all the way in the bottom. This is the ball, so I'm going to try to put it in there without losing it. There we go. And now we put the weight up. That's the weight. And also we'll do the other side. Very careful, because you don't want to lose this. And the weight. And then we're going to close that up with a screw. And note that there is no ring or O-ring on these screws. Often this is a point where people lose these little steel balls because they are so small. So next we're going to install the choke system or the cold start system. I don't really care about that one because I don't need this one, but some people might need it. So you have a mechanism here. and that should be working, that bolts onto the side that will lift actually the plungers. These are the two plungers, the springs that go inside, and the locking parts on top of the carburetor. And then you have the two choke jets, let's say, and they also come in a certain size. And I think we have an F565. So F5 again stands for the air opening, and the 65 stands for the fuel opening. Again, depending where you live, you may need more or less fuel being injected when it's really cold or not. So, first of all, we'll put the plunger in. That's one. And then we put the second plunger in. Then we put the springs up. And remember, the plunger goes in with the opening upwards. And we might want to push it down a bit. There we go. And there we go. Push it down. Good. The next thing is that we're going to close them up. With those things. And these are spring loaded, so you got to watch out a bit that it doesn't jump away. And we have a locking ring that goes on top of it. And you need to squeeze that a bit. Here we go. And then push it in. All right. Second one. There's some geese making noise. I'm living close to a natural resort, so these birds, you know, they always fly around this time of the year. All right, so that's done. And now we'll put the jets in. And these are the choke jets or the cold start jets. And I said before that I don't need those because I'm just going to depress the acceleration pedal a couple of times to do a cold start. That's how you do it when you are on a fast road car or a race car. You don't use a choke. That's for a daily commuter or in climates where it's extremely cold. All right, and now the last thing to do is to mount this panel on the side, and then we're all set. And now it's time to install the choke control mechanism. And there's no seal for this. It may be sounding strange, but that's the way it is. Let's put that in. Now I don't worry too much about this because I don't have any need for a choke. That works. Okay, that is done. Now we're going to install the bottom cover, and that one has a seal. Here we go. Oops. And let's try to put some screws through so we can hold the seal in place. And that's it. And this is the next part we need to talk about. This is the float. And the float is regulating together with the needle, the float needle, the amount of fuel that is inside the fuel chamber or the fuel well. So the level of the fuel. Very important for your emulsion tube to work properly. So let's have a closer look on this, on how this is working, and then we'll do the adjustment. Now imagine that the square box is our carburetor, and inside we have the float, and in my case it's a brass float. But newer models are using no longer brass, but they're using some kind of a polymer product, especially the Spanish Webbers are using polymer, but if you have a copper one, then you know it's an Italian one, and an early version. So my float that I have inside is a 26-gram float, and it floats actually in the fuel when it comes in. The fuel is coming in from the top, from the fuel pump, and you don't need a lot of pressure. That's a common mistake. You need about 0.15 to 0.20 bar, or 2.1 to 2.8 psi, so that's not a lot. But you need volume, and the volume has to be between 25 and 30 liters per minute. So you should get a fuel pressure regulator to make sure that you don't overpressurize it. Anyhow, so when fuel comes in, the level of the fuel will raise, the float will raise up, and eventually the float will push up this needle valve and it will close up the gap here so fuel stops coming in. So it is very important that this is regulated. Otherwise, we're going to have issues with our emulsion tubes, and we're going to be running too rich or too lean, all depending on what the fuel level is. Now, we also need to maintain the fuel level, and therefore, depending on the engine you have, depending on the engine size, more or less fuel will be consumed. And that's why you need to order up a needle valve which is fit for your car. Now, on my car, I have a needle valve which is 1.5 millimeters. Now, normally they recommend a 2.0 millimeter valve for a 500cc cylinder. I went for the 150, and the reason for that is if it's going to fill up and your needle valve is big, then it's going to go up and down a bit. You get this kind of little peak before it shuts off because it's filling so fast. With a smaller valve, you don't have that peak. You know, it's going to go up and it will stop very much in time where it should stop. Of course, you may run low on the level depending on how much fuel you're burning, so you may have to play a little bit with the needle valve. So the next thing we're going to do is install the needle valve, and there's also a washer associated with it. So if you change the needle valve, change the washer. Then we'll install the float and the seal, because you need to install the seal before you install the float, otherwise you can't fit the seal anymore. And then we'll verify if the float is still cutting off at the right point. So we'll measure it. Now the funny thing is that over time Weber has changed these values. So they talk about a float level of 7.5 and it goes up to 8.5. Somewhere you have to find the middle road. So I think I'm going to go for an 8, something like that, because that seems to be somewhere in the middle. And I can always adjust it later on. And that's about it. So let's get on with that. So if you're going to rebuild your carburetor, then you better always insert a new needle valve, and here is that valve, and mine is a 150. It comes with a washer. It's all part of the rebuild kit, and I'm going to install it right here. So let's do that first, and then we'll work on the rest. Turn it in by hand, and then I'm going to use a socket at the end. You don't need to over tighten this, okay guys? If you're going to reinstall the float, you need to check the weight, because it has a stamp on this lip and the stamp says 26 grams. So let's check it out and see how much it is. That's spot on 26 grams, so this float is still all right. So let's install the float. And for that, you have a little pin, and you need to push it in from the side of the support that is not split. This side is split, this side is not. So you need to push it in from that side. Otherwise you may break things. And let's see. There we go. Very gentle. And I'm using a big hammer, but you should not, right? I can't find my small one for the moment, so I'm going to take it very gently until that is it. All right? If you want to measure the float, you have to make sure that it's standing upright and that the lip of the float is just touching the valve. So it should not push the spring in, it should just touch it, okay? So that's important. And now we need to measure the distance between the seal and the bottom side of the float. There are special tools on the market that allow you to measure the float distance. You always need to measure with the seal in place. And what I see here is that I have with my tool, I measured around 8. And that's quite good. I'll check the other side as well, and that's also about 8. You need to check it at the bottom side of the float and make sure that both floats are lifted at the same level, because they may vary a little bit. And here you see the actual reading on my tool. So that's what I'm using to measure that distance. And now we can install the float or the cover on top of the carburetor. But we're not going to lock it down, because I still have to put the spring up after I've done the butterfly axle or spindle. And putting up the cover will be done with new screws and washers. But I'm just going to do it lightly now, because I still have to put the butterfly spindle up, and at the end we'll put a new fuel filter, and of course the inspection cover with a new seal. And mine, I painted it blue because my engine is blue, so that's just a personal thing. And the cover for the fuel filter with a new seal, always new seals when you rebuild something. And that's how it will look like. So we are finished with the baseline of the carburetor. We still have some mechanical work, the leverage mechanism, but also the spindle where the butterflies are on. And this is the new spindle. You might remember that the other one was actually completely bent and broken. We have new bearings, we have the original butterflies, and we'll put all that back to place. And that will be for the next video, where we're going to connect all the levers, where we're going to do some lever adjustment, and then how we're going to fit it on the block or the engine with the special supports. And that's for the next video, which is probably now going to be part number 2, Charlie, because this is a lot of work to do it all in one video. The carburetor is now baselined and assembled, and it's fit for purpose and fit for use. That doesn't mean that it does no longer need any more tuning. We will have to tune it further with test rides or on a dyno. I don't have a dyno, so it will be a couple of test rides. Nevertheless, we started off with the main venturi, and we decided what the size should be based on the engine and based on the usage. And I went for a 36mm main venturi. From the main venturi, we could calculate the main jet, and the main jet came around 145 or 1.45 millimeters. So I decided to crank that up a bit to have a little bit more of a rich mixture. I went to a 1.65. The emulsion tube that I selected was the F16, which has given me a bit of a leaner mixture at the lower revs and at slight acceleration. So this is kind of compensating a little bit for that main jet. And then my air reduction jet is now 1.75 millimeters, which typically you should have that about 0.5 bigger than your main jet. Now in my case it is not, but the combination of the main jet, the emulsion tube and the air reduction jet makes it probably quite suitable to drive. Again, a test drive will show how good or how bad that is. Once we got all that sorted out, we moved on to the secondary venturi, and there I decided to go to an opening of 4.5 millimeters instead of 3.5. Remember, the initial carb had a mixture of the two, which was not all that good. The next step was the idle circuitry. So the idle jet, we decided to go for a 50 F11. 50 meaning that it's the opening, or 0.5 millimeters for the fuel jet, and F11 is the opening for the air jet. It's all into one jet, and that seems to be suitable for a 500cc engine. Of course, that can vary. The acceleration jet is very important as well, so we determined that we're going to use an acceleration jet for the size of engine that I have, but I wanted to go on the low side, so it's going to be 0.35 millimeters. So that is not a large acceleration jet, but that's okay because you better start off lean. If it's not good enough, then I will put a bigger one in. We also looked on the bleed valve for the acceleration pump, and that's a 0.5 millimeter bleed valve, and in combination with the return valve. And then finally we started looking at the needle valve. I went for a 1.5 millimeter needle valve, so it doesn't fill up the carburetor that fast with fuel, so I don't get this oscillation on there. I may run a bit low on the fuel level inside the carburetor, maybe at high speeds, especially that we are running a fairly big main jet, but we'll see how that goes, and I think most likely we'll be all right. And then at the end we adjusted the flow to an 8 millimeter space, and that's about it. So I think so far we are quite good. So folks, we've reached the end of this video, and I hope you enjoyed it as much as I did, and we've done a lot of work and we've been able to baseline the carburetor. In the next video, which is now going to be 2 Charlie, we'll be talking about all the linkage and the adjustments that we need to do on the linkage. We'll install the butterflies on the carburetor, and then we'll mount it actually on the engine itself. What else can I say? Shit, I almost fell over. Oops, I shouldn't say that word, right? And remember, if you're going to baseline your carburetor, get a book. A book with all the details of all the parts, of all the emulsion tubes, of all the graphs, all that. You're going to need this because you can't do this without it. Now, I'm not making a commercial for this specific book, but it is very useful information. You can do your own calculations, but you need a basic set of information, and that's in these manuals. There are different manuals around. This specific one is from Weber themselves, which I found to be a bit better. But again, I'm not making a commercial for this manual, so on the side with it. So please provide any comments as you like, and I'm sure amongst you there are some good tuners out there that can correct me or improve what I've said, so please make those comments. And I hope to see you in my next video. Bye-bye.